So good morning, good afternoon, everyone, and thank you for the early ones who hopefully muted us when we were talking about some, non-webinar related stuff. But we're now on to the main program. My name is Annemai van der Meer. I'm the events director at Taus, and I'm very happy to introduce my colleague Andras Ponni. I hope I pronounced your last name correct. We have many difficult last names here at Taus, so it's hard to remember them all correctly. But Andras is the NLP research analyst here at Taus. As you may know, some of you have been following us for a while. Taus has undergone quite a change from the early days in 2005, when we were just a think tank, a think tank for the global language and translation industry. And now we've very much focused on the data side of the industry. So we have a couple of products and services in our resume that are very useful for the changes that we are seeing in the industry as well. And we're also pleased to have quite a large in-house NLP team who is working on novel NLP techniques, upgrading our data marketplace with exciting new features. And one of them is this text classification or domain classification that Andras will talk about today. So if we look at the agenda, it's a little bit different from our usual webinars. We start with a presentation from Andras explaining all about text classification with NLP. Then we have some space for Q&A. So if you have any questions about this first part, feel free to type them in the Q&A box here below or in the chat. We'll monitor both of those. And then after the first Q&A, we'll actually do a live tutorial on domain classification. Well, I say we, but Andras will take care of that. And after that, we'll have another Q&A for anything that you missed from the first part, the presentation, or from the tutorial. So with that said, I think we've handled all the practicalities, and Andras, the floor is yours.
Yes, so hello everyone. Thank you for the introduction, Annemai, and let us move on to the text classification introduction part. So I'd like to first begin with a little bit to talk about structured and unstructured data and why it is important to try to make sense of unstructured data. But first we have to understand what structured data means. And I'm just going to define it by saying that it is any kind of data that is stored in a fixed format that is somehow logically organized, for instance, in a table that you can then retrieve with a query. So this would be my definition of structured data. And then we have this on the one hand. And on the other hand, you have what is called unstructured data, which is basically any kind of data, and it can come in any shape or form that is not logically organized. So for instance, you can think about just a bunch of images on your computer, or a collection of documents that is not organized in any meaningful way. And in a lot of our industries that we work with here, this can be, for instance, translation memories, or user reviews, or even customer interactions. So basically, this can be just unorganized data. And we really have to find a way to make sense of this data, because otherwise it is possible that key business insights would be missed. So for example, we could learn market trends, we could learn trends about customer satisfaction, just by looking at unstructured data, which according to some estimates actually is about 80% of data that organizations are storing currently. So there is quite a lot of data that is going sort of missed. And one of the solutions to this is to use, especially for textual data, which is what we're talking about today, is to use natural language processing, or NLP. So what is natural language processing? So natural language processing, I like to define it as a subfield of data science, or a subfield of computer science that deals primarily with textual data. So I also like to say that it is the intersection of data science and linguistics. And you can basically deal with with language data at multiple levels. You can go from the top level where you have corpora, which can contain many documents, down to the level of documents, individual sentences. For instance, you're dealing with translation units when it comes to translation memories, which we often work with. So you'd have one sentence and its translated version in another language. And then you can also work with the level of individual words or tokens. And so basically natural language processing is a broad term that encompasses all of these different textual data formats, and it tries to make sense of this data. Some examples of NLP tasks that you might have heard about before are summarization. I believe recently OpenAI published a new model that is now capable of summarizing books into small summaries. So that is pretty interesting. And then we have text generation. Some of you might have heard about these models that are capable of generating really good quality text. And of course, we're all familiar with machine translation, which also falls under NLP. And then we have document classification. So I would like to give you a few examples of what document or text classification is. But to begin with, I'd like to just define classification. And the idea is simply that given any document of any length, you have the task is to assign it a label. And that label can be, when it comes to, for instance, spam filtering, you simply look at an incoming message, you look at the contents of that message, and then you decide whether it's spam or not. So that we would call a binary classification problem. When you're dealing with other sorts of data, for instance, user reviews, then you could apply sentiment analysis. This is also a form of document classification. Basically, given, let's say, a movie review, you can quickly and automatically analyze whether that movie review is positive, negative, or neutral, or this can be a product or service that it's referring to, and different sort of granularities are also possible here. And then the topic of today's webinar, domain classification, is actually what I'm going to talk about here in the next slide. So domain classification is basically the task of having a text and then applying a domain label to it. And why would you want to do this? Well, you would want to do this in order to be able to retrieve certain kinds of documents from a larger database without having to manually go and look for it. So if you have a large collection of data or documents, then you can actually retrieve specifically the kind of text that you're looking for by having these domain labels attached to them. But let's take a step back. First, we have to define the concept of domain. And this is actually not as easy as it sounds, because domain is a little bit of a fuzzy concept. It can mean quite a few different things. It often means topic or genre, but it can also refer to style. So for example, topics could be, when it comes to articles, for instance, it can be about politics or healthcare or medicine or gaming. So that would be classified as a kind of domain. Anima has already also mentioned data marketplace, where we have this domain hierarchy, where users can browse data based on different domains. And some of the domains that we have over there include business, services, healthcare, medical equipment, pharmaceuticals, but we also have domains called energy, education, finance. So anything you can imagine that any domain in which translations have been produced or are being produced, that is basically covered by our domain system. So what are some of the applications of domain classification? I would say, for instance, that it is very important in machine learning tasks to have the right domain when you're training your model, and then also to have that same domain in which you're evaluating and then deploying your model. So it's been, for instance, shown that when it comes to machine translation, if you have, for instance, you have a use case in which you would like to deploy a model to translate medical documents, you are going to need medical data to train that model. And it's been shown that models that have been trained on medical data perform better in a medical setting than just sort of general translation models. And this applies sort of more broadly in machine learning as well, which is perhaps not very surprising. And actually, as Anamai mentioned before, Data Marketplace actually allows users to upload and download, so to sell and buy data basically based on domain. So that is why at Taos we're using automatic domain classification to quickly label these data sets or domains, or sorry, documents rather. And so what are some of the methods of domain classification? So here we can separate them into three different categories. Three different kinds of approaches can be defined. The first is rule-based, which is basically based on linguistic rules or word lists. So the way this works is that, for instance, you would have a list of words that correspond to, let's stick with the medical domain, and then you use that word list to, if you have a document or article or sentence that you would like to classify, then you would, if you find the words that are contained in the medical word list, it is likely that the article is part of that domain. So you could label it based on words that it contains. That is just a simple rule-based system. Nowadays, we're using primarily machine learning, and that can be further divided into more than two categories, but here I'm going to discuss two categories. One, we have supervised and unsupervised machine learning. So a quick introduction to supervised machine learning would be that the idea behind it is that it relies on so-called ground truth, or the gold standard, which is basically a labeled data set. So you have, in practice, you would have your documents that you like to label, and then you would have labels attached to them that have been given by human annotators. And so this means that they are hopefully high quality. And by training a machine learning algorithm, which just means essentially showing that model hundreds or even thousands or hundreds of thousands of examples of what an article is or what a document is and what kind of domain belongs to that document, this model is going to learn the correspondences between article or document and label. And that is what we call supervised machine learning. Unsupervised machine learning is different. In that setting, you're not using any labels. What happens is that the model is trying to learn from the inherent structure of the data. So for instance, clustering methods are quite popular for when it comes to unsupervised machine learning. And we've been experimenting with that as well a little bit. Hybrid approaches, there's a third kind of approach. They are actually quite common in practice. What it could mean is, suppose you have a machine learning model that you would like to then tweak because you have a certain use case that you want to make it work for, then you could define some rules on top of your existing model if you would like to do that. And then that would be basically a hybrid approach. And I think with that, we arrive to the tutorial part, but before that, we're going to have our first question round.
Yes, so anyone who has any questions, something to clarify on this introduction to domain classification, type them in the chat or in the Q&A here. But one thing I thought would be good maybe to clarify, because both Andras and I indeed mentioned the data marketplace, which is something that we launched last year, November. And indeed, you say now, Andras, that automatic domain classification is something that we offer through the marketplace. But can you explain a bit more on just so that people get it clearly how it works? And in the meantime, we'll wait for other questions.
So basically, the way that works is that if somebody, for instance, you have a data set, a parallel data set that you would like to offer for sale, you can upload that to the data marketplace. And then you can also assign manually domain labels yourself, but we also have an automatic classification algorithm running in the background to sort of make sure that everything's okay. And we're also giving automatic labels. And then when data buyers, so let's say somebody, as I said before, you would like to train a specific domain, a domain-specific machine learning model or machine translation model, and you're looking for domain from data from a specific domain, you can simply click that tag, and you're only going to be able to see the documents that come from that domain. So you basically, it functions as a search function, basically.
Great, thanks. And we are receiving some questions now. So let me start here with one. Anders, you mentioned domains such as medical, education, but there are so many types of text contents in these domains, like patient information, leaflets will have very different linguistic features from medical research paper. So how useful is it to have such high-level domains? Is it useful?
Yeah, I think that's a good point. I think it depends on the application. In reality, yes, when it comes to dealing with language, we have many intersecting layers of and dimensions of information. So we can talk about domains and content types, and style and formality and informality. For what we are doing, we have this current hierarchy. But it is possible to define many different domain hierarchies and either intersecting with content types. And in fact, we are interested in working to always refine this system that we're using. And there's no standard, so I think every organization can make their own choice about how they're going to organize their domain system.
Yeah. Then the question about what's being used, or do you have any insights on what's being used in the market right now? Is it just neural, or yeah, can you share something about that?
In terms of domain classifier systems?
I assume so. It doesn't specify, but I assume, yeah.
Yeah, I think definitely neural networks, if that was part of the question, if I heard correctly, then they are, yes, very, very popular. I would say that I think the majority of platforms that offer something like this today are indeed based in machine learning, possibly some kind of neural network, but you will still find many rule-based approaches or many hybrid approaches today for different NLP tasks. So it's quite a mix, but recently the trend has definitely been to move over to machine learning.
Yeah. Thanks. Then another question. I could see great benefits in combining domain-specific MT engines with a workflow using domain classification to route a document to the best suited MT solution. Have you looked into optimization, such as at what point would you have too many domains in an enterprise setting and start suffering of the diminishing returns?
Okay. We haven't yet, I think, looked into it, but that is a very good point, and we would definitely like to. That is one of the things that I'm trying to do here at Taos is to find the answers to these questions, and they are very difficult questions to answer, but we're working on it. Yeah,
great. Anders, do you think more time for questions, or do you think we should move on to the tutorial?
I think let's do another question maybe, and then we can move on to the tutorial. Yeah.
Yeah, there are a few questions about examples and tools, like examples of rule-based and hybrid methods. Somebody asked about the techniques in domain adaptation. So I don't know if there's something else that you want to share about that.
Perhaps maybe that, of course, this is just a 1-hour tutorial, so or webinar, so I can't give you everything that there is to give. But I do recommend that you check out our blog, and we have an article on the Taos blog about specifically domain classification, where I go into a little bit more detail. And later on, I'm also sharing. We're also going to be sharing a GitHub repository with you, where you can also see this explained in a little bit more detail. Perhaps that can be helpful.
Great, yeah. So there are more questions, but let's indeed now move on to the tutorial, and then once we get through that, we'll return to the questions. And in the meantime, if you have more questions, feel free to type them in the Q&A, and we'll try to get to all of them at the end. And if we don't, then of course we'll get back to you via email afterwards. So
Yeah, and I'm
Back to
quite
you.
happy that we have so many questions. So let me move on here to the notebook. So basically, in this tutorial, I would just like to give you an idea of how to pre-process real quick a data set for domain classification. And then we're going to generate sentence embeddings. So we're going to embed this the data into vectors. And then we're going to train a neural network here, simple feed-forward neural network, which then we're going to evaluate and we're going to inspect some of the results. I hope everybody can see this. If not, Anamai, please let me know if there's an issue.
No, I can see it all.
Yeah. So as a quick introduction, I already mentioned we have a GitHub page that has been set up, also in connection with the article that's on our blog. And this is going to be shared with you after the webinar, I believe. And so as an introduction, I would like to speak a little bit about this data set that we're going to be using here. So this data set is essentially called BBC News data set, which is one of the sort of go-to standard toy data sets for domain classification. And it consists of articles that come from BBC articles, of course, that come from 5 different domains. As you can see here, they are business, entertainment, politics, sport, and technology. And they contain articles from these domains. Here, what I'm doing is I'm going to show you what this looks like now on my Google Drive. I actually split the articles into sentences here because, as I already mentioned, we're working mainly with translation units, which are essentially sentences. So for our needs, that is what we need. Sentence splitting is in itself an NLP task. So that is something I had to do with employing a trained machine learning model, but basically it returned sentence level labeled data. And this data set, of course, is publicly accessible. I have a link to it on GitHub, and I also explain how to do the sentence splitting. But let me show you what you can expect. As you can see, we have the sentences here to the left and their labels, and we have a bunch of different sentences. I believe there's 40,000, 42,000 altogether, and you can see that their labels are here. So we have sport, politics. What is important to mention is that these labels are actually coming from the level of articles. So the individual articles in the data set were annotated by humans and given these labels, but that doesn't necessarily mean that these sentences also really belong to that class, because by trying to classify sentences, that's a much more difficult task than trying to classify an article, which is perhaps not that difficult to understand why, since an article contains a lot more information than a sentence does. For instance, you will find a lot of sentences in a data set that don't really belong to any domain, such as congratulations, or something like this one here, number 47, or number 57 here. These come from an article that got the entertainment label, but that doesn't really mean that this sentence is really about entertainment. So we have to keep that in mind when we're training our model. So that's the data set we're working with. I hope I was clear. So let us now return to the notebook. So this, what you're seeing now is a Google Colab notebook, which basically allows you to write and share code. And to those of you that are familiar with Python programming, this is going to be easy to understand. To those that are not, I hope you can still follow. And I try to explain what is happening in each of these cells as I run them. And we're going to go through the whole process. Google Colab allows us to connect to GPUs, which is very useful because training machine learning models is actually a pretty resource heavy task. You need to have a lot of computational power, but this system allows us to do that in the cloud. So the first step is to import all the modules that we're going to use here. These are Python modules that I'm importing here, and already you can see if you work with machine learning that you TensorFlow here will be familiar. TensorFlow is a library that basically allows you to train neural networks and deep learning models with just a few lines of code. So we quite like using that. So that is the first step. And then after that, I'm going to load this data set. I've connected this notebook to my Google Drive. So basically this that I've just shown you is going to be loaded in here. I'm taking the sentences and putting them into a variable called X. And then all of the labels are going to be put into a variable called Y. And there's no reason why we're calling them X and Y apart from the fact that this is sort of convention within the data science or NLP community. So again, X is a container for our sentences and Y is a container for the category label. So if I run this cell, it's going to print the first 10 labels. I'm just double checking. And yes, it is indeed entertainment. If we looked at a different part of this data set, not the first 10, but let's say from 20,000 to 2010, then we're going to have sport. So everything has been imported. Good. So now what we have essentially is a bunch of string labels, which are not going to be very easy for the model to understand. So what we need to do this is we need to convert them to some kind of a categorical and numerical representation. And we're going to convert them to vectors. So for that also, I'm using another package called scikit-learn, where I'm getting this label encoder from, and I'm using this to encode the labels into vectors. So instead of having these strings, they're going to look like this. And this is what our machine learning model is going to understand. And so essentially what is happening here is that this label encoder is generating vectors. These vectors are called one-hot vectors because one of the values here is being indicated as 1 and the other ones are zeros. Remember that we have 5 categories, 5 domains in this data set. So I think this refers now to the entertainment domain because this is the first 10 examples as we saw before. If I change this a little bit, then I get an error, but this always happens. And then now we can see that the position of the 1 has changed, which means that basically I just mapped these labels to the vector here. So this is now the representation that we're getting. And we're going to have to do this for our sentences as well, because the strings cannot be directly fed to the model. So we have to encode our sentences. That's going to be in step number 5. So now we have encoded all of our labels. Now we need to split our data set into 3 parts: training, development, and test. And this often actually happens when you download or get the data. Sometimes these data sets are already split. In this case, this is not the case. I could have actually done this before. So this step could have come before this one. Basically, what we're doing here is when it comes to supervised machine learning, you have three kinds of data sets. You have your training set, on which you train your model. You have your development set, or often also called validation set, which you use to validate the model's performance, and then you can sort of tweak your model to get better performance out of it. But when you're finished with the experimentation, when you're finished with the tweaking of the model, you can test it on the test set, and that should be your final evaluation of the model. So ideally, the training set should be as similar in content or domain to the test set as possible. It shouldn't, of course, contain the same data points, but if you want to, as I said, if you want to deploy your model in a specific domain like finance, it should be trained on finance. Of course, there are ways around this, but we're assuming that this is the case. So here we're going to split this into 80% training, 10% development, and 10% test. This is pretty standard. Notice that I'm first splitting it into 80% training and then 20% development and test, and then I'm splitting development and test 50-50. And basically the sentences are being assigned into these sets randomly now. But when you look at the output, you can see that we have about 35,000 sentences on our training set, which is about 80% of all the data. And then we have about 4,400 in both development and test. So we can use this as a starting point. If we look at the GitHub, then we can also see how many sentences we have per category. So for instance, business would have about 7,000 in training. And this is pretty similar across all the categories. There's not big differences. I think the average is somewhere around 7,000, but you can see that technology contains much more sentences than entertainment, for example. So it's a little bit unbalanced, but not too bad. So now I'm aware of time as well. So let us move on to our sentence embeddings. I'm going to run this cell and I'm going to explain to you what is happening in the meantime. So just like I converted these labels to vectors here for the model to understand better, we need to convert our sentences into a vector, sentences into vectors each. So for that, we're using sentence embeddings. And I'm using this model published on TensorFlow Hub called Universal Sentence Encoder, which basically creates these sentence vectors that are very, very useful in NLP. Sentence embeddings are basically high dimensional vectors that encode semantic information. So you have these vectors in a so-called vector space, and you can perform all kinds of mathematical operations on them. So for instance, if you have two sentences that are very similar to each other, maybe there's one word difference, and you encode them into vectors, or you generate their sentence embeddings, then you will be able to compare those vectors, and you're going to find that they are very similar to each other. They will have high similarity. These embeddings, so this is what they look like. This is what one of these embeddings look like. Of course, this is completely, we cannot understand this. There's not much that this doesn't really tell us anything about the sentence. These are just a bunch of numbers here, a bunch of values, 512 of them to be precise. But it is very useful for the neural model because some semantic information is actually encoded in here. So now I actually printed the embedding of the very first sentence here in the data set. So basically now this has essentially become this, which now the model will understand, just like these labels have become a somewhat simpler vector. So now that we have all of our data vectorized, I think we can move on to actually building the network. And one more thing that I wanted to say about sentence embeddings actually is that we have also an article on the blog, on our TELS blog, which you can read, and there you will find more information about sentence embeddings and what they are and what they can be used for. But let's move on to the next step, which is building a neural network. So essentially, for those of you that are not familiar with what a neural network is, I would say, I would define it as a kind of machine learning algorithm, supervised machine learning algorithm, although not always supervised. But so a machine learning algorithm that is supposed to be modeled after the human brain. And so it has these neurons and connections. And this is also what forms the basis of deep learning. Deep learning is basically when you have a neural network with many, many layers in the middle. This is going to be a very simple neural network. We have 3 layers. So we have an input layer that is essentially going to read our data, read these embeddings and process them. Then we have one hidden layer, which is where all the weights are being then updated. I wish I could give you more about neural networks, but I'm afraid that it's beyond the scope of this webinar here. And so this is basically where the learning happens inside the network. And then we have our output layer, which makes the predictions as to what category each sentence is going to belong to. So I'm going to run the cell. Our model is here being built. And as you can see, we got a summary of the model. Again, this is one of the simplest models you could imagine, when it comes to neural models, it has about 19,000 parameters. Just as comparison, I think this large language model that just recently been published, GPT-3, I think it has more than 17 billion parameters. So this is a very small network. I hope I got that number right. But what we're going to do with this model, we're going to train this model. So let me run this cell here. Now, training or fitting the model, what does that mean? Basically, we're showing the model, the training set, and we're going to be doing that 10 times here. That is why we have 10 epochs. So the model is going through the training set 10 times, and it's trying to learn everything there is to learn about how the labels correspond to the sentences. Well, in reality, how the encoded labels now correspond to the embeddings. So it's learning that. As you can see, it's going pretty fast, thanks to the GPU here in the cloud. And so the model is essentially able to infer relationships between embeddings and their sentences and their labels, category labels. So now we're finished with training. You can see that the accuracy here has been increasing. That's on the training set. That's good. Also, I provided the development set here, and I forgot to mention quickly that we were calling these different sets X and Y also. So X would be the data points, and then Y would be the labels. And you can see here that already in the beginning, we had pretty high accuracy on the validation set. So this actually is improving a little bit, but not much. So I could have actually stopped training earlier. And then now, when we're happy with the model, we can move on to evaluating the performance. And now for that, we're using the test set, which is X test. I really should have mentioned this previously, but here I originally had my sentences when I split the data in S train and S dev and S test, and then when I converted them, that's when these variables X train and X dev and X test were created. So that is what you're seeing also down here. So now we're predicting we're using the model to predict a label for each of the sentences or rather embeddings in the test set, which is now here X test. And then we're going to take these predictions, and then we're going to compare them with the Y test, which is a container for all of the original labels, so the labels that we know to be accurate. And it's going to print a report here, which I'm going to explain what all the numbers mean. So as you can see, we've run the prediction on the test set. This is sentences that the model has never encountered before. There were similar sentences, obviously, in the training data, but these test sentences were not encountered by the model. And this little classification report here already gives us a lot of insight into what's happening. So let's have a look at this. You can see that we have our 5 different categories and the number of instances in each category in the training set. And you can see here on accuracy that we got 84%, which means that in 84% of all of the cases, the model was able to predict the correct label, which is already pretty good, given that we just had such a small, simple model. And if you want to break this down a little bit more, then we can also measure precision and recall, which are standard metrics in data science and also NLP. So precision and recall also answer questions about how well the model is doing. For instance, if we look at the class business or the domain business here, then precision would answer the question, what proportion of predicted business sentences are actually belong to the business category? So out of 100 sentences that the model labeled as business, how many are actually business? And according to the gold standard. And in this case, that is 83. Recall answers a different question. that answers the question, what proportion of actual business sentences were labeled correctly? So you can see that that would mean, again, it's the same number. So let's look at sport. That would mean that out of 100 sport sentences that had the label sport, the model was able to identify 91 of them correctly, which means it's already, I think, a rather well-performing model. And you can see that all of these classes are in this 80 range, which is why the averages of these are also 80, around 84. And F1 score is also on this report, which is basically a mean of precision and recall. So sort of just there to give us a quick overview. So I'm already quite happy with this model, actually, but of course you could make it better. But we have to keep in mind, as I said before, that this data set is originally a document level data set. So these labels that the sentence is actually inherited might not always be correct. So let's actually look at some of these sentences and let's see how the model does. So what I'm doing here essentially is I'm printing first the sentence, 100. I took 100 sentences from the test set at random. So I'm printing the sentence here to the left, then its actual gold standard label to in the second position here in the middle, and then on the right we have the predicted label. So as you can see, the model is doing pretty well, as we already know, but there are sometimes differences. So sometimes you would have a correct label here, but an incorrect prediction here. So let's look at this sentence. I always like to look at these sentences to see what is going wrong, because this is how you find out how to improve your model. So for instance, this sentence here, it will start 1200 GMT on Saturday and is expected to finish early next week. This is coming from an article that had the sport label. So the sentence also inherited the sport label, but now it's being classified as technology. But in reality, I would say that this kind of sentence is very difficult to classify. This perhaps doesn't even really belong to a domain. So for this particular sentence, this we might as well accept technology. Sometimes you can also see that the model actually gives a better prediction. I don't know if I can see that here. So for instance, we have business here in the gold standard, and we have a predicted label, politics. Let's see the sentence. The action, the biggest claim heard by employment tribunal in the UK, had been viewed as something of a test case. Interestingly, this could very well be politics. So it comes from a business article, but our model says that it's politics, and you could argue that this is actually a better label for the sentence. So if you look at these sentences, then you can see that most of them are actually labeled correctly. And I believe that's it for the tutorial. I have all the code here on GitHub, which again, we're going to share with you. So this gives you an idea of how to set up your data. I also have a link to the data set, how to pre-process the data, how to split it into sentences. There's a little bit of an explanation here to what's happening, and then how to train a classifier model. It is essentially the same code that we've seen so far with an evaluation. And I also have these metrics here. So with that, I believe we can move on to our second Q&A. And I hope that we will have some questions.
Yes, for sure. Thanks, Andras, for this. Well, myself, I was wondering, you mentioned that indeed there are some sentences that could actually belong to multiple domains, but there's also sentences that you wonder, does it belong to a domain at all? So what do you do with those sentences? Because are they then influencing the quality of the model? How does it work? What do you do with those short sentences like, I don't know, congratulations or things like that.
Yeah, certainly. We do have sentences like that, and that is why I said that it's quite a difficult task and perhaps impossible to categorize those sentences. What you can do is you can have an undefined category where you simply put all the sentences that don't really belong anywhere. And that is in fact what we are also doing, because there is no reason to put them into any domain category.
Yeah. So then a question here from the audience: how do you deal with unseen or new classes that may appear later?
For that, you would have to train a new model, because if we have a model trained for, let's say, 23 different classes, or you could have in this data set 5 different classes, then it's never going to be able to predict medicine or finance, because that is not in the training data. So for that, you would have to then acquire a new set of data and then train a new model. And that is how it would work, which is why these hierarchies, these domain systems have to be redefined at some point, depending on the needs of whatever organization is working with that.
So another question here, and that may actually even require a whole new webinar, but maybe you can explain in short, how do you turn each sentence into a vector? How does that work?
That does really require a completely new webinar. We're not doing that. We're using models that have been published and are publicly available. And this is quite complicated, but basically so these models that generate the sentence embeddings are mostly also either unsupervised or supervised machine learning models that are trained to perform some kind of an NLP task, and then this is basically the output. The embeddings are basically the output of the final layer of the neural network. That is one way to do it. And as I said, they are completely meaningless to us humans, but they are really good for computers, because they come from a neural network that efficiently learned that learned a representation of these sentences for a specific task in some of these models. And so it doesn't tell us anything. That probably wasn't a very satisfying answer. I would again point you to the sentence embeddings article, or there are a lot of articles also that are available online that do a pretty good job at explaining this.
Yeah, and I just, for everyone in the audience, I shared the link in the chat to the articles. You can already have a look there.
Yeah, no, but generating sentence embeddings itself is a big subfield of NLP, and a lot of research goes into it.
Yeah, and of course, there's quite a few questions about, did you look into this? Did you look into that? So yeah, this is an ongoing research, of course, Andres, right? It's never done.
Yeah, but we're very interested in looking into all of these things. So yeah.
Yeah. So one more question here. Did you look into tasks where training examples may have more than one label? So several topics. Was that part of the research so far?
Not specifically, but that is indeed possible. So you could perhaps, let's say, when it comes to domain classification, you could envision a domain hierarchy where you have literally a hierarchical domain system where you would have high-level domains, and then you would have lower-level domains. And indeed, in that kind of a setting, you could have a single document could have multiple labels. So it could be higher level label could be business, and then the lower level label could be I'm struggling to find an example now. Let's say higher level could be medicine, and then a lower level could be medical research, something like that. I'm not sure. That would be one example. of this.
Yeah. Then also, have you tried designing a model for classifying on the document level? And if so, can you share something about the obstacles in that?
Personally, I haven't tried that. I think that is actually, well, apart from some of these toy data sets. So if you do nothing to this BBC data set, if you just take the original articles without splitting them into sentences, then that is essentially the task you have. So the task at hand then becomes assigning labels to the articles, and that you will have much better performance than you saw on sentences. So I would say that there are much fewer obstacles than this level of sentences, because of the reasons what we discussed earlier about how sentences do not necessarily correspond to a domain. But one of the difficulties I could envision is, again, how do you represent an article? So for sentences, we have embeddings. We don't necessarily have document embeddings. Of course, you could generate them, and this is what happens in practice by taking either word embeddings or sentence embeddings and then trying to figure out a way to take their average. So for each sentence in the document, take and then get its embedding and then take the average of all those embeddings. Or do you want to concatenate them? Or do you want to do something completely different with those embeddings? You have to find out how to represent that article in a vector.
Yeah. Well, and then another question here is somebody who's a bit curious to hear from you what you think about this. As you were explaining as well, that classification resolves a lot of the polysemy, which is good for MT. But would it be also worth looking into the polysemous terms in a document in addition to the domains and topics? What do you think?
I'm not sure I understand the question. So looking into the polysemous terms in what way?
Well, maybe if Silvio is still here, I can open up your microphone. And so let me scroll down. He has already left, so we cannot ask him to clarify his question more. Yeah. That's okay. We have more.
I'm sure it's very interesting to do that, but I wasn't 100% sure what the question was.
We can talk about it another time. A question that came in earlier during your presentation, how do you estimate the reliability or consistency of the manually assigned labels? Some document classification tasks are inherently complex.
Yeah, it's difficult. So to estimate the quality of the label data set, that is the question, right? The human labels, right?
Yeah.
So I'm not an expert on this, on annotation, but one of the things that people do when they collect annotations is you would ask more than one annotator, so more than one person to annotate a data set. And then suppose you have a domain classification data set and you ask 5 different people to annotate the same data set, each document, and then you could measure basically what is called inter-annotator agreement, and what is basically a measure of how well they agree. So how similar, so if they give the same labels or not. And of course, if all the annotators give the same label to each document, then you're going to have 100% inter-annotator agreement, which is never going to happen. But you can get very high percentages, hopefully. Or honestly, I'm not even sure if this is measured in percentage. As I said, I'm not an expert in this, but you would do something like that. So you want to make sure that you have multiple annotators that agree and they give the same labels. And then if you have data points, if you have documents in this case that for which many different labels are being given by different annotators, that looks like they can't agree, then perhaps you don't want to include that, or perhaps you want to in your data set, or perhaps you want to call it undefined. I'm not sure.
Yeah. one question that that doesn't come from the audience, but from me, because of course now we are dealing with English, the webinar is in English. Are these models available for all languages, or can you share a bit about that?
Yeah, so it all depends on what kind of data you're training on. And this is not always true either. But so for sentence embeddings, what I just used here is for English, this model is for English, so it can give you sentence embeddings for English language sentences, but it also has a multilingual version, which can give you embeddings for 16 different languages. And then we have other models that we're also using for example, for data cleaning, that support more than 100 languages. So if you have such a model, then, or if you have sentence embeddings for multiple languages, then you can of course use those embeddings to train a model that can do a multilingual classification.
Great. One more question. Do you think that a transformer model will give better results?
Probably. I'm not sure. We'll have to try. Yeah.
Yeah, that's what I was thinking. It's probably not something that you can reply to here on the spot. You just have to experiment with it.
Yeah.
Maybe one final question in the last couple of minutes, which is a little related. What are your preferred, and it's a more personal question to you, Andras, what are your preferred Pythonic methods for training neural networks to handle word sense disambiguation?
So we're not explicitly doing that because this is, at least in my understanding, when you use sentence embeddings, then word senses are, depending on the embedding, but the ones we're using, the word senses are kind of being disambiguated by the fact that these embeddings have been pre-trained and then we're using these models. So when the models are trained that we use to generate the sentence embeddings, during that process, word sense disambiguation happens, and this is already contained within the embedding. So that is why we really like sentence embeddings, because they already do a lot of the work for us.
Great. Well, thanks, Andras, for responding to so many questions. There are more, but we don't have the time to go through all of them. So if you left your name, then rest assured we'll get back to you via email, probably in a day or two. Thank you all for joining today's session. We're back, of course, next month with another webinar. But in the meantime, you might also, if data is an interesting topic to you, you might want to join our virtual data summit on the 13th and 14th of October. We'll share more information in the recording email tomorrow as well. So again, thank you, Andras, and thank you all for joining, and have a great afternoon or day to all of you. Thanks.
Thank you.
Bye-bye.